So as you come in, start working on these problems. Okay, any comments about devotional? It was really good. Oh, Ryan said he called you out. Why? Are you hanging out in clubs throwing darts at the Salt Lake Temple? Oh, just some of the things you needed to improve on. So, okay. Any other comments? Yes.
My roommates last night talked about how they hated the beer ban, and then talked about the aggressive grooming standards while we're watching it. And I'm like, that's kind of awkward.
So that comment was, last night his roommates were talking about the beard ban and how they didn't like it, and then he talked about grooming standards today. So, yeah, it's very good. One last comment, if anyone wants. Okay. All right. Yeah, I think one of the principles that he talked about, if I remember this right, is like you shouldn't need someone to tell you that you know, not to wear a beard or not to do whatever or to dress appropriately. If you have the Spirit with you, it'll tell you what you should be doing, and you'll do those things. So there are medical reasons why. Like some people, they have skin issues and they should wear a beard. Like it really hurts them. So don't judge. Okay. Let's hit the homework really fast. So we are finished reading 3.5, read 3.6. I actually think we're spending 2 days on 3.6. Can you check the schedule? I think I made a mistake on this. So then watch the pre-class videos. I'll get those up after class today. So there's probably going to be a short one to finish 3.5 and then a short one on 3.6. Because we've already talked about some of the ideas in 3.6. It's all about linear transformations. We've already transformed BART quite a bit. So you guys will have some idea already about what's going on. And the written homework for 3.5b. Is that the one where there's only like one problem? No. Or did you guys already do that one?
That one's the one that has 2 problems.
Oh, that's 2 problems.
We were just debating, like, it says it has blind date scope, but it says it has 2
Yeah, so I edited it like the middle of last week, so I didn't tell the TAs, so that's probably why. So, yeah, you only have to do this 2 that are on there. I didn't know I had to do that. So did you catch that? Okay, thanks. All right, and then if you can send out an email to everybody, like both classes, about that issue that there's only 2 on there. Okay. Oh, it doesn't say 3.5. Let's get you guys started on this problem. You guys work like on this, and then I'll talk to Porter, and we'll figure this out. So. Yeah, the WebAssign won't, for 3.6 won't be due until, it's not due next time. We're just starting 3.6 next time. There's only one WebAssign. It'll be due next Tuesday. So, yes, Ryan? Yep, it's just really long. You don't have to read any, but I would just encourage you to start reading it because the finished reading 2.5 is going to be pretty light. So I'd encourage you to start reading 3.6 so it's just not so heavy.
We're gonna have to read the rest of 3.6 by the next.
Yep. Yeah. So that he asked if we have to read the rest of 3.6 before the one after that. Yes. So by next Tuesday you'll read the whole 3.6 and do the WebAssign. Okay. Sorry about that confusion. I had the schedule wrong in my mind. I didn't look at it carefully. Okay. You guys need more time on these? More time or more knowledge? It's usually one of those two. Sometimes you just need more time. Other times the time doesn't help. So, okay, we'll dive in. What's the rank of A? Why is the rank 2? How could you tell? There's a couple easy ways. Yes?
Well, first off, there's only 2 rows. The max it could possibly be 2. Yeah, 2 rows. So the max it could possibly be is 2.
Okay, so there's only 2 rows, so the max it could be is 2. Okay, it doesn't matter how many columns there are, like whatever the minimum number of rows, the minimum of columns, like whatever that minimum is, that's the most it could be. Okay, why not 1? Yeah. Okay, you said they're linearly independent. How do you know though?
You can't scale one to get the other.
Okay, if we're dealing with just 2 vectors, then we just have to check that one isn't a scalar multiple of the other one. And to go from 1 to a -1, you'd have to multiply by a -1, but then that means this would have to be a -2. It's not, so that's one way to know. Okay, very nice. What's another way you could decide that the rank is 2? One way to figure it out. Yes? Start row reducing and see how many pivot columns there are. You already know there's 1. You just have to see if there's going to be another one that shows up here. You just add the top row to the bottom row, make that a 0. This isn't going to be a 0. Boom. So you know that you have 2 pivot columns. Those first 2 columns are going to be pivot columns. Okay? So those are kind of the 2 quickest ways. What about if we multiply a vector x by a, we get out a vector b. So we're thinking about this equation, ax equals b. Where does x live? Which dimension does x live in? R1, R2, or R3, or R4, or R25? Scott says R3. Why?
Because if you're going to multiply it, you need 3 rows.
It,
Like have an x and a y and a z.
okay, he said if you're going to multiply, you need 3 rows because you need x, y, and z. This wasn't up when I gave it to the students in the last class. You guys already had you guys could cheat. But yeah, we've got 1, 2, and 3. Like we've got 3 entries here. We need to have 3 entries here to do the multiplication. Okay, so if you think about, we put on a context on this, so if this is peanut butter, bread, and jam, this is protein and fat. I picked the context after I picked the numbers. I know, so a -1 grams of fat and a -3. Is that what you were going to say? Oh, okay. So I know the context doesn't quite make sense with these numbers, but we're just going to use the context to help us make sense of what the multiplication means. Then what does x, y, and z represent? Like we're multiplying this by this vector. What does that represent? I know I should have erased this before, huh? This is the servings vector. This is the servings of peanut butter. This is the servings of bread, servings of jam. And these are grams per serving, each of these, if we pick that to be the units. Then the grams of serving times the servings will get you grams of whatever it is, protein or fat. So we start with a 3-dimensional vector, but what do we end up with? Yeah, 2b or not 2b? Just kidding. Yes? Is A a 2-dimensional vector? A like capital A? Okay, so like this matrix, we're calling this matrix A to make it easier to talk about. Is it a 2-dimensional vector. It means that it has two, the rank is 2. Like the information it has is 2 dimensions worth of information. So, but you don't call the dimension, you don't call the vector, the matrix itself a dimension. Like, what dimension is this matrix? R2?
Yeah, so on A, you asked, is X in R1, 2, 3, 4?
Oh, so where is A? So you can think about the matrix in 2 ways. You can think about where do the columns live, and you can think about where do the rows live. So you can think about this as 2 rows that live in R3, 2 vectors that live in R3. Or you can think about it as 3 vectors that live in R2. And sometimes it's valuable to think about it as one, and sometimes it's valuable to think about it as the other one. So, but either way, no matter which way you think about that, the dimension you're going to span will be the same. So you'll have, like the rank is 2, and that tells you like, oh, I'm going to have, if I think about it in terms of rows, I'm going to span a 2-dimensional space. If I'm going to think about it as columns, I'm still just going to span a 2-dimensional space. So here and then there.
So could we have made the X vector like a 3 by 4 and then it would have been an R4?
So the question was, could you have made this X a 3 by 4, and then would it have been an R4? They would still be, it would depend on the context. We still could do this. This could be servings for, what's your name? This could be servings for Haley. And I don't know if that's how you do Haley here. Okay. So here's our 2 by 3. We could do the servings for Haley, the servings for Scott, the servings for Ryan, the servings for Ian. Okay? And so, but each of these would still have to have 3. Like in the context, we still have peanut butter, bread, and jam, protein, fat. But each of these would still have to, you still have to tell me what you're eating in peanut butter, bread, and jam. So this still has to be 3 for us to do that multiplication. Okay? Yeah, and I don't know how to think about the dimensions like that, like like about this. But we can still get a matrix, right? And just each one of these columns would tell you about a different person, or a different day. Like you could do it per day or something like that. So, good job asking so many questions. Have you got more? Okay, there's one over here.
Yeah, I don't know if you had this or not, but we call him Big Answer the board.
Okay, Porta thinks he fixed it. So, okay, thank you. So, I did not intend that. So, I intended the opposite. So, okay. So, we're going from, you have to give me a point in 3 space, in R3, and we're going to get out something that we could put on R2. Okay? We need 3 coordinates for servings, but when we get out, we're only going to get something in R2. Okay? Find a basis for the column space of A. So someone tell me how they did that problem, if they were able to do it. Yes?
3 columns are independent, so, but since it's in R2, then you only need to pick 2 of the columns.
So you said they're independent? So we're looking at column space, we're thinking about 3 2-dimensional vectors. They can't all be, this can't be the set of these 3 can't be independent, right? But you're all right, you only have to take the first 2. But how would we know? We just need to take the first 2. Okay, so you can't just look, we can check and see if at least this is independent of this one. And they're not scalar multiples of each other. So I know those are at least 2 independent vectors. Then that's enough to span R2, right? I only need 2. So this has got to be redundant. So because I can already span all of R2 with these. Okay, nice. What's another way we could do that? Start row reducing. Nice. That's what I was going to do right here. So you can start row reducing if I add. Get 0, 4, 2. So at this point, I have a pivot column here, I have a pivot column here. So I need to go back to the original matrix and take those columns for the column space. Because row reduction can change the column space. I do row reduction though to figure out where my pivot, which columns are pivot columns. These two are pivot columns. So I go back and I can say the column space of A, the basis for the column space of A is the set 1 minus 1, 2, 2. Okay, questions? Yes? So the first and third would not be wrong. Like these could also form a basis. So you could test it by swapping these and then row reducing, and to make sure that that would also end up being a pivot column. So, but yeah, you are okay. If each of these are all yeah, I haven't thought of a really good explanation about that, but yes. So what this does bring up, a basis is not unique. Like there's lots of different ways to write down the basis of a space, right? The basis, a good way to think about a basis is it's a minimal spanning set for a space. It's the minimal spanning set. We need enough independent vectors that we span the whole thing, but we want the smallest number to be possible. If we're spanning R2, we need to have 2 independent vectors, but any 2 independent vectors is good enough. Ryan? Can I help write the book? I've tried. I only got 4 chapters into my book, right? You guys read it before you started class. I haven't got to this stuff yet. So maybe next semester I'll get to more. Over the holiday break, I'll try to write a bunch more. But there is power in the abstraction, right? There's power in understanding the abstract ideas. I just wish that the book and other teachers would start with a context to help you do the abstraction, right? So you understand what the abstraction represents. So.
Is it like a general rule, like you need two vectors, span R2, you need 3 to span R3, 4 to span R4?
Yep. So he said, is it a general rule that you need 2 to span R2, 3 to span R3, 4 to span R4? Yes. In fact, the way that we define dimension, they finally defined dimension in this book, although intuitively, we already have an intuitive idea of 1 dimension, 2 dimension, 3 dimensions. The dimension is the number of vectors you need in the basis to span that. So, but yeah, so R3, you need 3 vectors to span. And yep, anything else will be redundant. So it's the minimal spanning set. Yep. Good question. Sorry, I should have started off with that. Any other questions just about a basis, what a basis is? Oh, beautiful. Okay, I didn't even get to this in the last class, but I'll just do it at the beginning of the next class. So I actually brought up a couple weeks ago. I actually brought up a few examples when we were talking about spanning, and really they're important because they're a basis for things. So screen imaging, all of the possible colors you see on a screen, there's a basis for that, and there are those 6 values down here in the lower right-hand corner: the red, the green, the blue, and what the hue is, the saturation is, and the luminescence. And so those are the 6. So these are the basis things. Everything is a combination of these six qualities down here. It's easiest for me to just focus on the red, green, and the blue. You could do yellow, cyan, and magenta. Those are these 3 things here. But your eye has red, green, and blue. So they actually digitally, they just use red, green, and blue. But those are 2 different bases. You could do cyan, yellow, cyan, and magenta, or you could do red, green, and blue. Either of those are bases. You can't drop one without being able to miss colors, and any other color you'd add in would be redundant. You don't need it. The digital imaging, image compression, this is a basis for any black and white picture that you give me, any pocket of 8 by 8 cells, I can create with the combination of these things, these 64 things. These create a basis. And there are other bases, like you could just have we talked about this before, you could just have the one dot in each of the cells, and you can create anything by how shaded that one dot is, that one cell. But the advantage here is that pictures naturally will do things like this up in this corner. They rarely do things like this, so you usually don't need them, or if you don't include them, they don't make much of a difference. So it allows you to get all the information, or almost all the information, with a lot less data. Like you know, with about half the numbers you need to include. And then sound waves, a basis for sound waves is sine waves. Any sound wave you give me, I can make or get really close with sine waves. So then that makes it easy for me to reproduce that sound, or to store that sound on a computer, or to convey that sound. Does that make sense? Does that help? Yeah, so these are 3 kind of real world applications where we have a basis for things. There are others, but yeah, these kind of like come alive for me. Like these are like my favorite examples. I feel like they capture well. Okay, what about the row space? Find a basis for the row space of A. How did someone do this? Ryan? He said there's only 2 rows and you need both of them because they're independent. We know that because when we start row reducing, we have a pivot position in each of these rows. Okay, here's a pivot position. Here's a pivot position. So we need both of them. So which one should we take? Like these 2 rows or these 2 rows? Or should we keep going? Or these 2 rows? They all work. So row reduction can change the column space, but it does not change the row space. These two, all of those work as a basis for the row space. So I could do 1, 2, a -3, and -1, 2, 5. Oops. Yeah, so I could do that one. But I could also replace those 2 with these 2, or with these 2. All those are fine. Over here, and then there. No, it might depend on the application. Usually these are simpler to think about, and I'll show you on GeoGebra why. But the further down you go, kind of the more you're reducing. And here you have to think about x, y's, and z's. Here I just have to think about an x and a z. Here I just have to think about a y and a z. So I'm kind of like constraining them more. So sometimes, if you think graphically, this is often better, but you don't have to pick one. Ryan? Yeah, so the question was, does it matter if we write them as column or row vectors? You should write your columns as column vectors and your rows as row vectors, okay? Because that portrays the kind of vectors that you're dealing with. So, yeah. Okay. All right, now the hard one. The null space of A. Find a basis for the null space of A. It was fun? Oh, good. Okay, so I don't know if everyone agrees with Ryan that it's fun, but I'm quick question, I want you to do thumbs up, sideways, or thumbs down based on how confident you were with this, finding the null space. So thumbs up if you were good. Okay, thumbs sideways if you're like, well, I think I got it, or some things, and then thumbs down if you're completely lost and you're not so sure. Okay, great. Well, not great. It'd be great if everyone's thumbs were up, but I did see lots of thumbs up, lots of thumbs sideways, a few thumbs down. So the null space is the set of all vectors x such that that arrow, that's supposed to be an arrow. Mathematicians are really lazy. I mean, most people are, but mathematicians are really lazy, so they don't like to write more than they want to, so they make up notation. So that means such that. See, it's a lot easier to do that than write such that. Sometimes they'll do s dot t. So all vectors x such that ax equals 0. Okay. So if we find all the vectors that we can multiply by a on the right side and get 0, then that's in the null space. That is the null space. So this is just a system of equations we've dealt with before. So let's augment our matrix with 0 and row reduce. I didn't augment it yet over here. I row reduced, but some of you have already figured this out. If I went back to here and added zeros and row reduced, what's going to happen to that last column of zeros? It's still going to stay 0, no matter what row reduction you do, what row operations you do, they're just going to stay zeros. So I'm going to come down, 0, 0. That's not true with everything, right? If they're non-zeros, then you'll get, it can change. And I can rewrite this as a system of equations. So that means I can rewrite this as x minus 4z equals 0, and y plus 1/2 z equals 0. How many free variables do I have? 1. Here's a free variable, okay? Because I have x, y's, z's, okay? This isn't a pivot column, so z is a free variable, so I'll let z equals z, okay? And then I'm going to solve for x and y up here, and I'll just have z, all my z's on the right. So I'll have x equals 4z, y equals 1/2 z, z equals z, negative 1/2, thanks. And then I'm going to, if I pull z out, then I just get z times the vector 4 minus 1/2, 1. Okay. So if I'd asked you, what's the solution to this system, ax equals 0, where this is the matrix A, then that's something that you should have been able to do, or that we worked on 3 weeks ago or 4 weeks ago. And we would have done this, we would have got this, and you would have described the solutions as all x, y, z's, such that t, so t times 4 minus 1/2 and 1. Okay, so replace our z with t, so we don't have z serving 2 different functions. We pick a parameter here. This is what we get. Often in those problems, these weren't 0. When we asked you to solve a system of equations, we didn't just have zeros over here, and then you'd end up with some other constant thing over here that wasn't multiplied by a parameter. But since we're going through the origin, that all of those are 0, so we can just delete those. Okay, so the null space is this line. So this, we have a vector, we can multiply it by any scalar. That describes a line, right? It's a three-dimensional, it's it's a vector in, it's a single vector in R3. So the line will go through R3 somewhere. But the null space is that, one way to describe the null space is it's that line. Any value that we can get by, any vector we can get by multiplying this vector by a constant, then we'll get 0 out if we multiply this by that vector. Right? Do we get 0? Do you guys trust me? 1, 2, minus 3, a minus 1, 2, 5. If we multiply by 4, a minus 1/2, and 1, do we get 0? The 0 vector? 4, minus 1, minus 3, 0. A minus 4, a minus 1, so that gets a minus 5, plus 5, 0. Yeah. What if we multiply everything by 2? Okay, so that's 8, 1, 2. Negative 1, 2, thanks. Okay, so now we have 8 minus 2, so that's going to be 6, negative 6, gets a 0. A minus 8, a minus 10, 5 times 2, 0. So now we're really just dealing with scalar, how a scale interacts with a dot products. We could prove that would work. But yeah, any scalar multiple of this doesn't matter. We're still just going to get zeros over there. So, and matrix product, we could write it as A, C, X, and you just, well, that's C times A times X, right? We know this is, we convinced ourselves this is true. And if X is in the null space, that much is 0 vector, so you just get the 0 vector, because C times 0 is 0. So different ways to make sense of that. Okay, so a basis for the null space is just pick this vector. You could pick this one too, doesn't matter. So basis for the null space is the set 4 minus 1/2, 1. Okay. All right, I have any questions? So the goal from here on out is to make sense of what that null space means. So let me, I'm on the wrong thing here. Should have prepped better between classes, but someone had to go to the bathroom. We won't mention any names. Okay. Oops. Close your eyes. I'm giving it away. Where it is. Okay. All right. So we're focusing on row space right now. So these two black vectors, okay, they're pointing to points A and B. Those points or those vectors, they are these two vectors here. Okay? So if we row reduce them, I claimed that it doesn't matter which of these two that you take, the span of those will be the same. They'll still be the basis for the same subspace. So if I take these, 1, 0, negative 4, and 0, 1 1/2, I get those two red vectors. And it looks like they all line up right there, don't they? So I could try to do it that way too. It looks like they all line up. You might convince ourselves a little more if we put the plane on there. So this is the plane. This is the plane where that's the span of the black ones, and it looks like it's this, those red ones lie in that same plane. So one thing that's kind of cool, so if you look at it from the top, so this blue, the blue is the Z. The grayed out one is the XY plane. So the gray plane is the XY plane. I can't remember which one is, well, we should be able to figure out which one is X and which one is Y. Which one's a negative 4? Looks like red is X. So yeah, there we go. So notice those red ones, they lie on the x-axis and on the y-axis, right, from the top. And that's because one of them has x equals 1 and y equals 0. The other one has x equals 0 and y equals 1. They still have z components. They still go up and down from there, but we're looking at it right on top, so we don't see them go up and down. But once we move it like that, you can see that. Okay. So when we multiply this vector times this matrix times a three-dimensional vector, we go down to 2 dimensions, right? We go from 3 down to 2. It would be really nice if we only put serving sizes here that lied in this span. It would be really nice to do that, because then we'd have 1 point and it would just go to 1 point. We're dealing with a 2-dimensional input and it would go to a 2-dimensional output. But that's not the case. We can pick any input in this space, right? There's no restriction on what serving sizes you have to eat for peanut butter bread and jam. I'm going to pick G. So I'm going to put G on there. So G is another spot. G tells me where I'm going to go. So G is my protein and fat. So if you think of the XY plane as an outcome, then it's protein and fat. F is my servings, where X is the servings of peanut butter, Y is the servings of bread, Z is the servings of jam. And so if F is the F, that doesn't make very much sense. But then I lose G if I lower my servings by a -0.3. Okay, let's not talk about the specifics. All right, so here's a point F, and once I multiply it by that vector, I get a point G. Okay, and there's G. But if I'm going from 3 dimensions down to 2, that means that there are a lot of points in R3 that have to go to the same point in R2, in our output. So my question for you is, let me put F right over here. Well, maybe right there. That F goes to G. Where are all the other points in R3 that go to G? So think about that for a second. Where would all the other points be that go to the same place that F goes? There's got to be lots of them. In fact, there's probably infinity of them. Where could they be? The null space, someone says. Okay, Ryan? Are they on the normal line to that point? Okay, so we have 2 options. So someone said the null space, and someone said the normal line to that point. You guys are both correct in a way. So the null space, so the null space is a vector. Where'd my null space vector go? Oh, so right here. This is just one vector, and it describes a line. And I'm going to put that on here. Where is it? Null space basis, right there. Boom. Okay, look at that. What does it look like? Yeah, it's through the origin, right? The origin has to be part of the null space, right? Because it's 0, 0, 0. And so if you have 0, 0, 0 as x, you've got to get 0 out, right? And it's normal to the basis for the row space of A. Okay? And if we take F and find all of the points that project, whose projection is F, and projections are orthogonal, right? Then all of those points will go to G. Will go to the same spot. And that because the null space basis is orthogonal. Where's my line? It's got to be at the top. Okay, so there's F. Look, it has the same slope as the null space basis because they're both orthogonal. To project down to F, you've got to go orthogonal to that plane that it's on. Okay, so any point. Okay, so question so far. The basis for the null space. A basis is a set of vectors. So this is, I wrote it right over here. So it was the question is, how do we write the null space, or the answer, and it's this. So a basis is a set of vectors. So I wrote it set notation with that one vector. So so any vector, sorry, any point in, oh sorry, any other questions before I move on? Yes.
Is there like a notation to write the basis of the null space or the basis of beta, something like that, or do you just write that?
Maybe. I can't think of one off the top of my head. That's why I just wrote basis for null space. Yeah. So they'll just start writing script B for bases. Like they'll just start calling a basis. They'll just start naming it with scripts. So they're often script B. So any point in R3, any of our inputs, okay, can be written as, so this is like a three-dimensional, where our inputs are in three-dimensional space, right? Any of our inputs can be written as some point F on the blue plane, and some plus some constant times the basis for the null space, okay? Because this describes the line. So if I go to the point, and then I look at that line perpendicular, I can get any point in R3 with this, right? Finding some point on that plane, where F represents any point on the plane, on that blue plane that spans the row space, and then the normal space, okay? What happens if I multiply by A? So what's the normal vector here? I'm sorry, what's this N? It's the null space. What's special about the null space? It's the null space of this matrix. A times anything in the null space is 0. This is the basis for the null space. It's in the null space. So that much is 0. The 0 vector. C times that is just going to be 0. So it's just the same as A times wherever that point got projected to on it. That perpendicular projection. Anyone here from American Fork? I had a kid in my class. I already knew he was from American Fork. So, okay. All right, what happens if we do, here's a new matrix for us. We won't have time to do this together. 1, 2, minus 3, minus 1, minus 2, and 3. Okay, so this first row is the same. Bottom row, it's linearly dependent with the first. It's a constant scalar multiple. Yeah, it's a constant multiple of the first one. So what's the rank here? 1. How many free variables am I going to have? 2. Rank plus free variables equals the number of columns, equals the dimension of the input. Okay? And that's, so rank plus nullity is 3 in this case. Nullity is the dimension of the null space. Like, we have a bazillion different ways to say the same thing in this class. I know it's probably really, really bothersome for you right now. So if we row reduce this, we just get 1, 2, a minus 3, 0, 0, 0. And if we get, let's do it. So if I want to find the null, a basis for the null space in this case. So it's going to be 2 dimensions. I can rewrite x plus 2y minus 3z equals 0, but I have 2 free variables. So these x's and y's are free variables. So y can be whatever y is. Z can be whatever z is. And I can rewrite that, and I get x equals a minus 2y minus 3z plus 3z, y equals y, c equals z. And that's all the same as, if I pull out my y, I can rewrite that as a minus 2, 0, oops. Minus 2, 1, 0. Z is z times 3, 0, 1. Okay? So the basis for my null space for this matrix are these 2 vectors. Any vector I can write as a combination of these 2 vectors, when I multiply it by this vector, by this matrix, will be 0. Okay? Here and then there. Okay? Yeah, so let me pull up, this is the example over here. So this is the vector, that black vector is, that's this 1, 2, and a negative 3. So that's a basis for the row space. The row space looks like a line. So we don't get a plane this time, it's just a line. And now, if you put a line that's perpendicular, all the points that lie on a line that's perpendicular to, that lie in a plane, that's perpendicular to that line, they will all go to the same spot as the 1 point on the line that they go to. So the dimension here of the null space is 2, so the plane, so they span a plane, and those 2 vectors, those 2 purple vectors are these 2 vectors. Okay? So anything in that plane will go to 0. But if I was able to shift that plane up and down this line, then any point in that plane would end up going to the same spot as the point where that plane intersects the row space. So, what was that? Yeah, when we yeah, in the mapping, in the multiplying of this. Okay, there was a question? If you guys need to go, you can go ahead and go. But yeah, what's your question? That's right. So he said, if there's no free variables, then the only null space would be the origin. That is correct. And the row space, the row space would be all of R3, or it'd span the whole thing. Nice job.